German people will say the same.
So I will try and talk a little bit about some of the experiences that we have had testing different turbulence chemistry interaction models in an LES context. And to understand the basics a little bit better, I'm going to start showing you some of the applications that we are really interested in computing. And let's start with aero power generation gas turbines. These are the typical configurations that you will find in the industry. This is a helicopter engine, and this is more like a slightly generic power generation gas turbine. And they're typically composed of a number of burners mounted in a ring. And the burners are usually extremely complicated, since especially for aero gas turbines you're burning a liquid fuel, a long hydrocarbon chain, kerosene, JP8, something like that, Jet A. Whereas for power generation gas turbines, natural gas or something else is typically what people are using, but if you're looking in power generation on ships, they're even interested in oil. So, I mean, this is quite complicated. And some of the really challenging issues here is that when you have multiple burners like that, they will interact with each other through the acoustics. And you will have combined longitudinal, radial and azimuthal acoustic waves here. And if you are able to look into some of these configurations, they have sometimes portholes that you can actually look into, for example, by fiber optics or something else. You can see really how these flames flap, and occasionally they can stop burning. One or two neighboring each other can stop burning, and so on. And this will create a lot of emissions. And this is, of course, what you like to be able to minimize. So this is extremely challenging to compute. And these are problems that we're actually trying to work on and to simulate and study the various kinds of effect here. And these two are computed with between 60 or 80 million grid points, something like that. And it takes quite a long time because some of these instabilities that you have take a long time to develop and have fairly long time scales associated with it. And also the geometry can be pretty nasty. This is one of the burners situated here, with a lot of small, very narrow channels, and you better try to make that pretty decent modeling actually. Otherwise, the results will be quite incorrect. Another problem that we are working on is condensed phase explosions. So this is an explosion that goes on quite close to the surface, and you're looking at one of the species that is evolving and also the resulting shock systems. And there you have a lot of additional physics like Rayleigh-Taylor, Rickmeyer-Meshkov instabilities in the afterburning phase.
Is it chemical?
This is a TNT explosion, AGMX explosion. So it's pretty standard. It's not a complicated explosive, but still you have a lot of physics there. And what they're interested in is putting particles and droplets and have a really multi-phase interactions in there. And the third area is supersonic combustion in terms of ram and scramjet engines. This is a model of a high-shot 2 engine, which is one of the few scramjet engines that has been flying around for a couple of seconds at least. So this is the variety of problems that we are really trying to address. And it's going to be extremely challenging if we need to have very different models for all of these different regimes. So we're actually looking for a combined modeling framework based on LES to tackle these questions or these problems. as I've said, there is a lot of complex issues associated with these problems. Complex physics, for example, liquid film breakup, atomization, vaporization, shocks, different types of instabilities. You have the complex geometry that you need to handle. And we don't believe that RANS models, steady or unsteady, are really able to incorporate all the interactions with the additional physics there. Some of it might be possible to include, but definitely not all of it. So we need to look at more advanced models. This goes, of course, with a lot higher computational costs. DNS, I guess that's quite on the expensive side for these kind of problems, so that's out of the question. So LES is really what we are trying to do, or what we're trying to deal with here. And for non-reacting flows, LES is reasonably well established, but for combustion, it's not that established, and there are a lot of issues to be concerned with, and you heard about some of them already here. There is the subgrid flow modeling, the combustion chemistry, how much chemistry do you need to put in there, and also the turbulence chemistry interactions.
You said that RANS doesn't work. Does it mean that mean field approach at all doesn't work here?
I mean, these problems are completely unsteady.
Because there are no separation of scales, time scale and special scales? Why it doesn't
No,
work?
simply because, I mean, if you look at the gas turbine engines there, you have acoustic waves that travels back and forth in the entire combustion.
The mass number is not so small.
Well, for the gas turbines, the Mach numbers are small, but for the scramjet and the explosions, the Mach numbers are pretty big. So you need to take into account all this unsteadiness.
Yeah. But for slow processes.
Yeah, but I mean, for the cases that we looked at here, there's no way that you can deal with quenching of flames and things like that. So what I was planning to do here is basically to talk about a few cases that we have been testing different turbulence chemistry interaction models on. A lot less complicated than these ones. Cases where we have experimental data to compare with. And just to put things into perspective, this is typically the regime in which we have experimental data from laboratory. And this is up here somewhere. We have most of the applications. So there is a big gap in between. And I don't think we have any good clue about how to close this gap, or to how to extrapolate from the models that we developed down here. So this is difficult. This is a dump combustor. This is a low swirl burner. This is a gas turbine combustor, can combustor, and this is a afterburner model. These are the four cases that I will talk about a little bit later. But first I will try to describe the LES approach. And what we do in LES is that we try to simplify the problem. These are the equations for non-reacting flows that we look at. This is a schematic illustration where you have eddies and various scales. And what you do is that you apply some kind of spatial filtering, so to try to remove the small scale eddies and replace them with, or the effect of them with models in the equations. Hopefully it will describe some of the features. And primarily it's the energy dissipation that we're after.
And what is E, excuse me, what is E? It is energy.
E, that's the total energy.
Total.
Total energy.
Total energy.
But when it comes to combustion, the situation is quite different. Now you have additional equations, one for each of the species with reaction rates, and that's where the chemistry comes in. And you have a flame situated on the grid, which is typically pretty thin, highly wrinkled. and it cannot be resolved on an LES grid. That's general situation. The main flame brush, however, these lines out here, they have to be resolved well on the LES grid. So that's the kind of scenario that we're looking at.
But ideology of LAS is based on some kind of mean field approach. In some sense, because you...
Well, a mean field approach in the sense that you're removing the small scales and only try to retain the large-scale energetic motions.
But you have some parameterization in small scales. In any case,
Yes,
it
we
doesn't
have
imply that you remove.
We have models here.
Yeah. So this is a mean field approach.
I'm making that
In
sense.
some sense. Of course, in LAS you don't have separation of scales. You have filtering scales.
Yes.
That's it. But nevertheless,
Nevertheless, it's some kind of averaging.
Yeah.
Because filtering is averaging.
Yes. I mean, we're removing the small scales, and
Right.
that is filtering, and that is then in a sense averaging.
But you are resolving the flame front, so in that
Yes.
sense you are...
Yes.
No, we're not resolving the instantaneous flame fronts.
Just
We're resolving the flame brush
Oh, I see.
and some of the wrinkles that
Mhm.
appear in the flame, but not all of the small scale wrinkles, because the edges that are actually wrinkling the flame are removed. So that's a parameterization, and that's a model.
Yes. Okay, right.
And this is actually the turbulence chemistry interaction models that is essentially the main theme here. And this is, of course, the issues that we're facing: the composition change, the exothermicity, the volumetric expansion. All of this comes from the chemistry, which is on the molecular scales, essentially. The reaction rates are strongly non-linear, especially with regards to temperature. Another issue is the reaction mechanism. I mean, if you're burning simple fuel or complicated fuel, there's a lot of intermediate products, and that might change things. So that's something also to be a bit concerned with. And essentially there are two different classes of models: flamelet models and finite grade chemistry models. This is a crude grouping of models, but this is one that you can deal with, and I will come back to that later. So regarding the chemistry, I put some numbers here. For hydrogen-air chemistry, you need, say, 8 species and 38 reactions. That's the most recent to describe it reasonably well. For methane air, you need about 50 species and 300 odd reactions. For C12H23, which is like kerosene type, you need 500 species and several thousand reactions. No way that you can put this into a 3D unsteady code. So this is the really a big challenge. We need to be able to find ways to simplify the chemistry without losing the important information. And we need to develop some kind of understanding for and tools for developing reduced or global reaction mechanisms. And I would say that today we can handle something like 10 to 20 species. Beyond that, it's going to be on the expensive side for these kind of complex problems.
And number of reactions is not so important, right?
The number of reactions is not that important, but it's the additional equations that you're solving. And there is also this issue. I mean, you're simplifying the fluid dynamics, so that's an error you're introducing. But you're also simplifying the chemistry, so that's another error. And how do we balance these errors in a reasonable way? That's hard to understand. We have adopted one approach from Meredith and Black, in which they have a detailed reaction mechanism, and they use some kind of optimization algorithm to reduce this detailed mechanism into a much, much simplified mechanism. That appears to be a reasonably okay approach, but then you're limited to rather narrow ranges of equivalence ratios. That's kind of a problem. If you move from one regime to another, the coefficients need to be changed. But, I mean, since we have practical problems to solve, we also have to find practical solutions to these kind of things.
You mean an Arrhenius form you should change?
Everything can be in a generalized Arrhenius form, yeah.
The species also.
So, here we will, for the cases that I will be presenting, we will be using a three-step hydrocarbon air mechanism, which essentially comes from this approach applied to the GRI mechanism. So it will be consistent whether it's methane or propane. So if you're looking at the reaction rates, they're highly nonlinear. We're talking about the Arrhenius reaction rates. And there are essentially at least three ways to conceptually deal with this and understanding. One way is simply that you introduce this decomposition into filtered fluctuations into these expressions and apply all the algebra that you can figure out and try to rewrite the equations in a similar form. And then you will find an expression like this with terms, very complicated terms, that include the effects of the fluctuations. This was done a long time ago by Foreman, Williams and others. But in an LES context, it's going to be different because they will also appear beneath the filtering bar, so to say.
What type of closure is used when?
We're not talking about any closure yet. We're just talking about how to try and understand these nonlinear interactions.
Yeah, but you have higher moments.
Yeah, I will come to the closures later on. The other way to look at this is say that, okay, what I have accessible during the simulations are the filtered species and temperatures. How can I reformulate these equations in that way? And you can do that by just introducing a correlation coefficient like this. Then it becomes a lot more handy, so to say. But this term is going to be extremely complicated. It will contain all the issues, basically. So that's probably not a very useful way either. The third way is to use a probability density function, like this. So you can write the filtered reaction rates using a probability density function. And then you either have to compute it using a transported PDF type approach, or make an assumption how it looks like. And this is going to be function of all the species, temperature, and density. Not really a straightforward way that either. So we have to try and figure out something else. But we have at least, I think, tried to look at the problem and see the different issues with it. So if we turn to DNS and experimental data and the physical information that we have available, and I think this is something that we need to look much more closely into, because here you have all the physics either measured and interpreted or computed using DNS. And I think this is an area where we need to do much more analysis that can really help us understand the physics that goes on. So these are some pictures that I've collected. This is a DNS calculation of Paul Woodward on a very high Reynolds number flow using, I think it's 496 cubed simulations. And there you can see vorticity, you can see it in terms of sheets, you can see it in terms of ribbons, and you can see it in terms of tubes that are interacting. And if you zoom into this on a small region where the arrow is, the physics become a lot more rich. So there is a very wide range of scales. And a lot of these tube-like structures, they agglomerate and act together like vortex filaments. The second picture here comes from Tanahashi's DNS calculations. So you have a flame situated here, you have vorticity on the background, you have exothermicity or heat release in the yellow regimes. So you can look at that and try to analyze what goes on in there. One of the things that you find is that you have exothermicity that occurs between the so-called fine-scale structures composed of these vortical structures that we have here. So looking into some of this data, probably just a fraction of what's available, we can see that we have a non-uniform spatial distribution of fine structures in these turbulent flows. You have vortex sheets, you have ribbons, you have tubes, these kind of structures, all of them essentially associated with the polymonomer scale, either in terms of the thickness of the sheet or in the radius of the ribbon, for example, or the radius of the tubes. These fine structures are responsible for much of the dissipation and some of the mixing. They tend to appear in strained regions between larger flow structures, larger eddies. And as we've seen from the DNS, reacting DNS, the exothermicity appears to occur in between these kind of structures. So this is some information that we can deduce from DNS and experiments. And another approach to closure modeling in terms of combustion is actually to try to build physical models out of this. I have a few slides describing different types of models that we have been working on. The first one is, of course, a flamelet model. And in the flamelet approach, you essentially replace the species equations with equations for reaction coordinates, normalized temperature, normalized mass fraction, for example, and a mixture fraction if you're dealing with partially premixed or something like that. And you couple that to a flamelet library, as we saw before. Or if you prefer to use the G equation, you have a G equation together with a mixture fraction and another type of flamelet model. So this is the framework, and then you apply different kind of closure models. For example, for the C equation model, you have to prescribe the flame wrinkling factor. It was on the one before that, or the flame surface density. They are closely related to each other, so you can translate between one formulation to another. And there exist algebraic versions like this one, but there is also differential equations describing both the flame wrinkling and the flame surface density. And for the G equation model, you have a similar type of situation. You have to describe the influence of the turbulent combustion and how the laminar flame speed varies with mixture fraction and stretch, for example, in this case with a PDF.
Could you remember what is Z?
Z is the mixture fraction.
Mixture.
Yeah. And I mean, this was just two models that I almost arbitrarily picked. There is a lot of them, and I'm not sure that these are the best, but these are the ones that we have been using in these calculations. So if we tend to the other class of models, finite rate chemistry models, I have three different finite rate chemistry models that we have worked on. And the first one is the thickened flame model. It's currently a quite popular model, and it's based on the work of O'Rourke and Bracco. And they essentially found that you can use the flame speed and flame thickness to rescale the flame thickness so as the flame speed is going to be preserved. And this was in the 80s perhaps, late 70s, beginning of 80s, something like that, in the Proceedings of the Combustion Institute. Then, much more recently, in the 90s, Pauline et al. And friends they developed this approach for LES by essentially thickening the flame, artificially thickening the flame so that it will survive on the grid. And the key thing then was to preserve the laminar flame speed. If you thicken the flame, something will happen with the flame speed, and they definitely want to preserve the laminar flame speed. So they retain the species equations, and these are the equations that they're solving for a given chemistry. And what they then do is that they observe that the turbulent flame speed is proportional to the laminar flame speed with an efficiency function, or flame wrinkling factor. And as the laminar flame speed is proportional to the reaction rate and the diffusivity, the thermal diffusivity, you can use that to reformulate this equation so that you will have an effective diffusivity and an effective reaction rate. Whereas here, this F factor is the thickening factor. So this will preserve the turbulent flame speed.
What does it mean, effective reaction rate? So
you will basically, you will be reducing your reaction rate with a factor of F.
Yeah.
And then you will essentially increase your diffusivity with a factor of F. This is what they're doing. And they actually plug that into the species equation. So you will have a slightly different formulation for the effective diffusivity, and you will have an effect on the reaction rate, which is a division by the flame thickening factor and the multiplication of this efficiency function. And the efficiency function is chosen so that it will take into account the scales that you have removed while doing this artificial thickening. So that's one currently quite popular approach to deal with this. Another one, which is the eddy dissipation concept. This was developed by Magnusson. It was developed essentially for RANS in the late 70s. But we and others have also applied it to LES and slightly reformulated it. And this approach is quite different in that it's based on the physics to a slightly higher degree. Here you recognize that what happens in a typical LES cell is composed of fine structures and surroundings. So you actually postulate balance equations for the species mass fractions and for the temperature or energy that account for the interaction between the surroundings and the fine structures.
What is tau in this approach?
Tau is a timescale. So far it's...
What timescale?
We will come to the timescale, the definition of timescale. But it's a timescale. It's associated with a small scale.
Can you please explain? It's a dynamic timescale or chemical timescale?
I will come to that. Those details we will come to.
This is tau approximation.
In some sense. The question is what weight, how it is built.
What you then do is that the LES filtered mass fractions, temperatures, they are related to the corresponding values in the fine structures and surroundings using this ratio, fine structure volume fraction essentially. So if you introduce that expression into the previous one, you're left with these sub-grid balance equations. And they contain two quantities, gamma star and tau star, that needs to be prescribed from somewhere else. They need to be modeled somehow. And this is a time scale of this, which is associated with the small structures, and this is the volume fraction of these small structures. And yeah, let's continue that. What Magnusson then did was that he worked on the cascade process model, which is very well described in the paper. So they have essentially a model of the cascade process that is coupled to the inertial subrange process. And from that, they deduce velocity, length, and time scales associated with these small-scale fine structures. And there is, of course, a model coefficient, which you can close essentially from the dissipation model that you're using. So the coefficient here from LES is going to be quite different from the one in the RANS context. But this is quite straightforward.
This is only for velocity field or also for the...
This is only for the velocity field set. So this is a way to get this time scale. So in that sense, it's a hydrodynamic time scale. But we're still left with this gamma star. We haven't said anything about that. And in the papers of Magnusson, he introduces this fine structure reaction specs. And he ties that to the physical interpretation of that you have tubes or sheets or ribbons, etc., building up the fluid. And for them to react, the temperature needs to be sufficiently high. And he essentially postulates that this gamma star is going to be proportional to the velocity V star divided by the fluctuating velocity field squared times a fraction of the heated structures. And he gives an expression for the fraction of heated structures, but he doesn't really explain how to get there. And
This is some kind of feeling factor of these tubes.
feeling factor.
Feeling factor.
Not this one. I mean, he explains that in terms of some of the structures cannot react due to the temperatures not high enough. In that. So,
Some kind of intermittency.
well, I guess this is the intermittency.
Yeah.
Yeah, this is intermittency
Yeah.
factor, yeah.
So the equations that we're left with solving for the species equations are the usual ones, with the reaction rate now formulated in terms of the temperature and species mass fractions of the fine structures. So this is not the filtered temperature, the filtered mass fractions. These are the ones in the fine structures. And you get those from solving these equations. And you're multiplying it also with this fine structure function. And of course there will be another term which is 1 minus gamma star. But that one is usually very small compared to this one.
Go close to 1 million.
No, but the values in the surroundings of the temperature is usually significantly lower than within the fine structures. And the reaction rate then drops dramatically. So you can typically neglect that. This is the second model of this kind. We have worked also with another model, partially stirred reactor model. It draws on what Magnusson has done, and it draws on what Wallis has done. And it's a slightly different approach, but it has many similarities with Magnusson model. The issue with the subgrid balance equation is there. We notice that we have small-scale structures, sheets, ribbons, and tubes. We have fine structures, we have surroundings, and we propose to use the same type of subgrid balance equations to compute the small-scale temperature, small-scale mass fractions. But then we do it slightly different. We notice that we have to take into account, we have a time scale there, and we also have to deal with the fine structure, volume fraction, or intermittency. The time scale here is modeled as the geometrical mean of two time scales. One is the Kolmogorov time scale, which is the smallest time scale, and the other one is related to the shear, the large time scales. Delta here is the typical grid size. V prime is the characteristic fluctuations.
But chemical time can be smaller.
Yes. And then we also have a chemical time scale. Either you can compute it from the chemistry directly, then you will have a range of chemical timescales, one for each reaction, or you can simplify life by using an expression like this, where you have a thermal diffusivity and the laminar flame speed. So far we have done it this way because it's simpler.
This is molecular thermal diffusion.
Yes. Yeah. The next issue is to deal with the reacting volume fraction. And Magnusson does not really explain his postulate. So instead, we have based this on the information available in the LES cells. We have a velocity scale, we have the different time scales for chemistry and for the flow essentially. And you have an area that surrounds these small-scale structures. So this is essentially the ratio of the volume enclosed by these small-scale structures and the entire volume available in the LES cell. So one of the things that we looked at here was that we were able to reformulate this expression for the reacting volume fraction and compare it with the situation where you have pure tubes or pure sheets in that cell. And this expression will give you a value which is between sheets and tubes. And it will vary as the Reynolds number varies between sheets and tubes. So it will be more sensitive to what happens in a typical cell than, for example, the EDC model. I think this is quite an interesting part of the model. The question is, can we somehow improve that based on DNS data or experimental data? Or can we, so to say, verify it? We have not looked into this.
Delta, what is it? It is grid of you
Delta is the typical grid.
of your LES model, right?
Yes.
And
Or the
B
filter size.
dash, it is typical velocity in this
Yeah.
grid.
Physically, you have sheets and you have tubes. Tubes related with electricity and sheets.
That's also vorticity.
Yes, it is.
You will have
Plane
sheets of
vorticity.
vorticity.
Plane.
I mean, two-dimensional model.
But it's a little bit strange, of course, this idea. For me, it's more natural to replace to start by T dash, tau dash, tau start by tau dash, because it's how you feel from a Kolmogorov scale, if you average. Strange.
But here you can see that you have both sheets, which are semi-transparent, and you have very intense vertical structures. So you can really see this in this DNS computations. That will, of course, be strongly affected by chemistry, which we have not taken into account. This is just more like a mental picture that we build this upon. So these are the equations that we will be solving. They're very similar to the EDC model. The reaction rates is evaluated at the fine structure, temperature, and species mass fractions. And we have this reacting volume fraction and intermittency factor in front of it. So I will be comparing results from these models for 4 different cases to see if we can learn anything about how the different models behave. All of this is done in one code. So we're using an open source code called OpenPhone. It's a C++ library that you can essentially download from the internet. And it comes from the Thermal Fluids group at the Imperial College in London originally, and it's now released under a GNU license. And the cases I will be talking about are all subsonic. So the code that we're using is based on this library, and it's an unstructured pilot volume discretization, multi-step, essentially Crank-Nicholson time integration, a piece-of-type pressure velocity handling. This works for subsonic flows, but not for supersonics. It's fully compressible, You have essentially linear reconstruction of the convective fluxes and interpolation of the inner gradients. So it's second order accurate on the nice grids, so to say, but it will of course degenerate when the grids are really bad. And it's fully parallelized. So the first case I will be comparing results from is a simplified, very simplified afterburner test case studied experimentally by Volvo Aero here in Sweden. And it's a rectilinear channel, essentially. You can see it in the lab here. You have a triangular shaped flame holder. You have propane air coming in this direction. They have two different operating conditions. The first one is at a Reynolds number of about 45,000, and the inflow temperature is 288 Kelvin. And this is the one that will go on the top pictures here. The second one is slightly preheated, 600 Kelvin, and Mach number of almost 90,000. And it will go down here. This is roughly what the flow looks like. And in this schematic, there is a small picture showing the structures just behind the flame holder. These two different modes of operation are going to be very different from each other in terms of how the flame develops. There is some very nice sharing images and animations from the experiments where you can see these very different kind of flame flapping developing modes here. And one thing is clear, and that's all these four models, thick and flame model, EDC, partial stirred reactor, and flamelet model, are able to capture this difference in behavior from one operating condition to another. So this is not essentially related to the combustion model, but primarily to the fact that you're taking a lot more of dynamics into account when you do an LES computation.
And this LES computation depends strongly on filtering scale?
And the filtering scale enters, it enters the combustion model, it enters the subgrid flow model as well.
Yeah.
And when the grid is finer, the effect of it disappears. So when you refine the grid, the effect disappears, so it goes asymptotically towards the DNS. Here you have comparisons for these two operating conditions, the non-preheated and the preheated case. Here we're looking at normalized axial velocity at 3 cross-sections, quite close to the flame holder, somewhere further downstream and even further downstream. It's based on, the experiments are LDV measurements, and the agreement for all of the cases, with the exception of the flamelet model, is pretty good in the first cross-section here. If we move further down, there is a lot more spread in the simulation data. Here we can see, for example, for this case, that the flamelet model over-predicts the length of the recirculation zone. It's going to be a lot longer in this case than compared to non-reacting flows. Whereas the thick and flame model under-predicts the length. Further downstream, towards the end, we can see that the flamelet model still has some low speed region towards the center retained, so it hasn't really recovered yet. Whereas the other models show a reasonably good trend to capture the velocity field here. Similar situations for the other case. Then we have also temperature data to compare with. And we have two different temperature data sets. One is coarse data, and one is gas analysis based data. And the first thing that we notice is that the gas analysis data and the course data are different. And they are very different.
This is experimental data?
This is experimental data. So now, when you talk to the experimental guys, you might get different answers to why this is the case. But it appears that most experimental people, they tend to believe more on the course data than on the gas analysis data. So we should probably compare more with the course data than with the gas analysis data.
Which is which? Which is which?
The pluses or the crosses are the gas analysis data. You have them here. Whereas I see what you mean. The circles are the course data. You
How
have
will
them
they take it then?
in here.
This is data. This data for the same experiment of the top,
Yes?
just using different measuring technique.
Measurement techniques.
Okay.
How was this gas analysis data taken by local sampling? Or?
Oh, I don't know, to be
Uh-huh.
honest.
Yeah, but it must be because it's a profile, right?
Yeah, it's local, but I don't know the details. But
Mhm.
we can probably look it up somehow if you're really interested. But it was, I think it was a probe that you traversed through the. But it takes some time and it can continue to react and things can evolve. That's the best explanation that I've had from experimentalists. And what we can see here is that, again, the flamelet model is slightly under predicting the temperature, the width of the combustion zone, so to say, in this case, whereas in this case it's pretty good in terms of the width, but it's slightly over-predicting the temperature, at least in this cross-section here. But the general trend, I think, it's pretty okay.
Have you also tried different subnet modes for the velocity field?
There's a lot of parameters to play with.
Yeah, I know, but how sensitive is the chemistry is the most important, or the velocity field model?
To be honest, we have not turned that knob for the reacting flames. I mean, I work with other areas as well, like ship hydrodynamics, and then the subgrid model is the key thing. So we have based the combustion modeling on the best available information we have from flows around ships, which is of course dramatically different. But there we were interested in the boundary layers and small-scale turbines. And the model that we're using is one equation in a viscosity model, sometimes coupled with a scale similarity type term as well. The few tests that we have made on combustion doesn't really show that this is an important contribution.
On the flamelet model, it doesn't seem to work as well. Is this possibly because this is with a G equation, you do have to put a flame speed on the surface, and we don't ever know what to put on the flame.
We need to talk to Bai about that tomorrow, because this was done in collaboration with his students, and this is their G equation model. And we have had a lot of discussions about how to formulate things, how to implement things, etc., etc.
But it may not be a bad approach, it just may need additional information.
To be honest, it should work, because this case is in the corrugated flamelet regime, so it shouldn't really be bad. But what I'm interested in is in some kind of modeling approach that works for a range of conditions. We get similar type of information from CO, which is one of the intermediate species that we also have measurement data on. The next case is an axisymmetric dump combustor that was studied by Gold and friends. And this is the device. You have the combustor, you have a contraction, you have a blower here, and you have fuel that is added to the air. And now we're talking about methane. And then you have some kind of extension duct, which is water cooled. And this is a snapshot from the simulations. You can see that you have a cold, so to say, reactant-rich region that is persistent almost throughout the combustor. So mainly the combustion occurs in this regime here, and you have a hot region towards the walls. And looking at some of the comparisons, now it's exactly the same finite rate chemistry model, but now this is a C-equation flamelet model, so it's not really the same flamelet model. You see that all the finite rate chemistry models using very good agreement with the data, whereas the flamelet model kind of over-predicts the velocity, the high-speed velocity region, and especially out here, so it essentially over-predicts the exothermicity from the chemistry, or it over-predicts the flame speed, so to say, the turbulent flame speed. For this case, we have also temperature or velocity fluctuations, and they're also in reasonable good agreement. The velocity fluctuations from the flamelet models are slightly too high. You can see the green here, whereas from the fine rate chemistry model, well, they're slightly on the high side, but not as high as from the flamelet model. We get the overall profile reasonably well, which indicates that the burning regime, the flame brush, is reasonably well captured. It's in the right position. The spreading is right. This is the temperature profiles. Again, we have reasonably good profile agreement, and also the evolution of the profiles is pretty well. The temperature, especially for the flamelet model, is slightly too high in this regime. You can see that also for the partially stirred and the reactor and EDC model. So there is something that goes on in this regime here which is not perfect for these models. Looking at the temperature fluctuations, which I would say is a pretty rare quantity to have access to, that's mainly why we chose this case. We see very similar agreement as for the velocity fluctuations. The flamelet model over-predicts the temperature fluctuations, and that is, of course, how it can handle the dynamics of the flame brush and the interactions between the non-reacting flame and the shear layers with the combustion cells. The next case is a lot more complicated. It's a low swirl burner studied in Lund, experimentally studied in Lund, and it's based on the Robert Cheng's burner. And this is essentially from the burner itself. You have an inner and outer tube here, and between them there is 8 swirl vanes. In Robert Cheng's experiments, I think he has 16. Here you have 8 swirl vanes. Upstream of that you have a plate with a lot of small holes in it. And before that you supply the fuel to the air. So this is essentially pre-mixed. And you have warm air coming outside as well, but the temperature is pretty low, so it's 10 degrees above room temperature or something like that. And in Lund they did simultaneous OH, PIF and LDV measurements. So this is LDV measurements, and these are the laser-induced fluorescence measurements. So this is the fuel, which is mapped by an acetone tracer. And this is essentially the flame sitting here, so this is the red regime. And they have some very nice animation showing how this region of the flame behaves dynamically, and there are some very interesting structures that develops here.
So this is distribution of number density?
Yes, it is, essentially. And this is a corresponding picture from one of the Morgelli simulations. You can see that this is different instance of time, of course, but you can see different types of structure with roughly the same sizes developing in this regime. And one of the first criteria that we looked at was where is the flame actually stabilized. So this is the computation. You can see the lower parts of the flame sitting here, and you have the velocity coming around it. You have a lot of turbulence that is generated inside of the burner because we compute all the way through the swirl vanes. And experimentally they measured the standoff distance to about 0.64 diameters. And the partially stirred reactor and EDC model were able to predict that standoff distance very well, in fact. Whereas the two other models, they reasonably well predicted it. Some adjustments had to be done with the flamelet model because in that case you had to adjust some parameters of the turbulent flame speed to be able to capture the standoff distance. So this is axial velocity cuts in these cross sections here. And you can see that, especially for this case, the thickened flame model starts to behave pretty bad some distance downstream of the burner ring. Slightly further downstream, the flamelet model also starts to become slightly different. It spreads out a little bit too much, whereas the experiments, they show these very nice structures that are evolving.
This is mean velocity?
This is time average data. Time average experimental data and time average simulation data.
For fluid velocity.
For the fluid velocity. And similarly for the RMS fluctuations. Now we see that essentially all of the models overpredict the RMS fluctuations by almost 50%, some of them. In this regime down here, but this is also a regime that is extremely difficult to measure because of the interactions with the nozzle. Slightly downstream, the agreement becomes a lot better, with the exception of the thickened flame model, which shows some turbulent fluctuations even far downstream. We see a tendency in the data to have a smaller circulation region somewhere down here, so it's quite far away from where the flame is, this part of the flame, but it's downstream there somewhere, and it's a pretty weak recirculation region.
This is LDV data?
This is LDV data, yes. Similarly for the azimuthal velocity profiles, we have both axial, radial and azimuthal velocity and RMS fluctuations, so we have a lot of data there to compare with. And we also have a fuel distribution from the acetone cliff that was done. That data is much more scattered than the velocity data. The data points are not as close together, and we can see that some of the models, in this case the flamelet model, shows a much wider spread in the fuel mass fraction, and it essentially shows that all the way from the beginning and throughout. And we're not really sure why we have this issue here. You can also see that the thickened flame model somewhat over-predicts the flame speed in the core, so that it consumes the fuels a little bit too fast. So essentially what happens is that the flame is too close to the nozzle ring compared to the data.
This is mean number density?
This is converted into mass fractions, but they're of course not, not the experimental data.
I see.
Yeah. But otherwise, I mean, everything is converted into mass fractions. And I think this is a quite difficult case to compute because that you need to be able to predict this distance very accurate. So either you have to sort that out by dealing with the flame speed properly, or, as in the other case with a finely grade chemistry model, the chemistry does that for you. The chemistry predicts a turbulent flame speed that is reasonably accurate. I think this shows that this approach is actually working in this kind of global sense. The last case I have is the Tors burner, triple annual research swirler, which was studied by Effie Gutmark in between 2000 and 2004. It's it's a gas turbine fuel atomizer essentially, and now we're talking about something that is even more complicated in terms of geometrical complexity. And the simulations that we have done, they include the swirler and all the details. And for these cases, you have an inner swirler, you have an intermediate swirler, and you have an outer radial swirler here. And the fuel is supplied through these holes here, in that channel and in that channel. And here we're talking about gaseous propane air combustion. So we need to be rather careful in gridding this up to have enough resolution to deal with the internal shear layers, and so that these jets are actually distributed in a reasonable way here. This is a snapshot. You can see the flame. You have a central recirculation region that develops here. You have toroidal recirculation regions that develops between the flame and the combustor wall. This is vorticity on the center line. You can see that there is a lot of structures developing in these mixing regimes. The flame will be roughly anchored somewhere here. You have this as the toroidal shaped vortex region, and you will have a central recirculation region in here. And it's the balance between these recirculation regions that stabilizes the flame essentially.
This recirculation, what is it actually? It's a result of chemical phenomena?
Sorry?
Is it chemical phenomena, this recirculation? Or,
No, it's
or a result of, say, jet? I don't know.
It's essentially related to the swirling jet. So this is swirling. And when you have this swirling jet, you have vortex breakdown, especially when you have swirl numbers like 0.55, I think this was something like that. So you have vortex breakdown, and then you have the central recirculation region developing.
So it is a dynamic phenomenon, sir?
Primarily hydrodynamic phenomena, yeah.
Due to chemicals.
For example.
And this is some of the data that we have. Mean velocity, time average velocity field in 5 cross sections. First one is pretty close to the dump plane, and the other ones are following down. I think this is like 4 or 5, 6 diameters downstream. I think the last one is. And you can see that all the models does a reasonably good job. You can't really discriminate based on this. Similarly for the axial RMS fluctuations, again, for all of the RMS fluctuations that we have looked at, the spreading is larger and the discrepancies are slightly larger as well. Some of this might be attributed to the fact that we're not sampling for long enough, because the second order statistics take forever and ever to get right. But I think this is reasonably well sampled because all the data is symmetric. This is some of the azimuthal velocities. And now we're starting to see some differences here. First of all, we note that the experimental data is not symmetric on the center line of the combustor, which we expect it to be. And this causes a lot of concern in terms of the experimental data and so on, but it is very difficult to make measurements in a combustor like that.
And how stable is asymmetry? Is it change from experiment to experiment?
I don't know. We have discussed this quite a lot, but I'm not really sure. I don't think they have made very many experiments for exactly this operating condition. I think they have looked at different operating conditions.
They measure here derivatives of velocity field, shear or
They're measuring the velocity field itself.
Maybe?
LDV and thermocouples from the temperature. So there's also temperature data to compare with. Unfortunately, the temperature data is at some distance downstream. They couldn't measure essentially where the flame is. So the temperature data is down here. And it's not really that helpful because what the interesting thing is really what happens in this regime here. On the other hand, it looks like, at least on the on average, we have some flame left at this cross section here, whereas the experiments don't show any local decrease in temperature here. So it looks like essentially all of these simulations might over-predict the length of the flame somewhat. If this is a chemistry issue, modeling issue, or something else, it's different to say because this is quite difficult to deal with. And also there is an outlet here which is not very well described. We know that there are acoustic waves in this combustor, longitudinal waves. And how the impedance conditions in the experiment match the ones that we have in the simulations is an open question.
how many parameters
In the LES models. For these cases that I've shown, we have 4 different models, 3 final grade chemistry models that we can clearly talk about that are exactly the same for all these 4 cases. We haven't changed any parameter in the models. For the subgrid flow model, there are 2 parameters that you can play with, if you like. These are computed from the inertial subrange spectrum, from analytical integration of the spectra, essentially, and left that. So they're hard-coded. We don't modify that at all. For the combustion, I just went through the details of the combustion model. There are essentially no parameters left to play with. There are no constants or nodes that you can play with. So in that sense, I think this is a reasonably okay framework to operate with.
Is the time it takes to run these models about the same or some longer?
No, I mean these are roughly the same. The flamelet model is faster, of course, because you have one reactive scalar to play with, whereas you have 6, 7 species equations. But it's comparable. So this is what this is some of the concluding remarks. We're trying to compare predictions from both final grade chemistry and flamelet models for 4 different flames. I think it's very important that we look at different flames for one particular model, and as different as possible in some sense, to see if we can understand under which operating conditions it works. There is data for all cases, and the key thing is also that we have used the same code with the same numerics, everything the same, for 2 of those cases. The other two cases we used a different code with a G-equation model, whereas we used the same code for the final grade chemistry models. So the frameworks with regards to numerics and solving equations is the same, which is also quite important when we're comparing models. We have also made sure that we have as similar laminar flame speeds as possible, the ones that are actually provided in the flamelet models, and the ones that we obtain from the final grade chemistry models that we have put in there, the reaction rates. It appears from these 4 cases that we get better predictions from the final grade chemistry models throughout all the cases. Sometimes the differences are very small, sometimes the differences are a little bit larger. It is quite difficult to tell, and to rank models is even more difficult. looks like the partially stirred reactor model is always, it always gives acceptable results. It doesn't really stand out predicting one of the cases less accurate than the other models. It appears to be a quite robust and quite stable model. I think that the thick and flame model rests on a little bit questionable grounds. There is not really the physics put into it, but on the other hand, there is scaling arguments that are sound. So that's also difficult. The ADC and partially stirred reactor models are conceptually very, very similar. It's only the time scales, when it comes down to implementing things, it's only the time scales and this reacting volume fraction that is really different here. And to conclude, I think we need to look much more closely into this issue. We need DNS data, we need high quality experiments. And I think we need to work together, both fundamental work and applied work, so that we can test hypotheses, models on more complex cases like the ones that I have here. And there is a lot of good data out there for these cases. Thanks.
You haven't mentioned what you use as boundary conditions for the inlet flows in your different cases. Do you use some kind of plug flow or what fluctuation?
I have to stay away, try to stay away from something. Boundary conditions is really an issue. I mean, we have near wall boundary conditions where you would like, if possible, to resolve the structures that you showed and how they are interacting with each other and with flames if the flame is in the proximity there. Typically, you cannot do that in LES. I will come to that. So we're using a wall model, and for some really high Reynolds number cases, we combine that wall model because it's valid in a certain regime with local grid refinements. So that's one thing. I think we have reasonable information to believe that works. The inflow and outflow boundary conditions are much more difficult to predict. And the first thing is that if you have an experiment, you're given an experiment in a wind tower or whatever, which part of the experiments are you going to try and put in the computational model, basically? So where are you going to choose to have an outflow or an inflow? That's the first crucial thing. Then you have to try and understand if there is acoustics that affects things and so on. The second thing is what to prescribe in the inflow and what to prescribe in the outflow. The outflow is difficult because if you have any acoustics there, you will have an acoustic impedance condition. And you need to try and have some information from the experiments about how that looks like and try to do something similar in the computations. We're typically using these Poisson-Lene type boundary conditions, and there is a free parameter there that we can adjust to give or to emulate different acoustic impedance conditions. And for some cases we have really tried to scan a range of impedance conditions to try and match experimental data. Not any of these cases, but other cases. And this can be a really difficult issue. Regarding inflow, I think it's important to try and compute through, for example, a fuel injector and so forth, as far away from the flame as you can basically afford. And what we have, I mean, the information is typically mass flows. We don't have any profiles or anything, so typically fixed mass flow or something like that.
With no fluctuation.
With no fluctuations, because you will have the fluctuations from pulsing through the swirl. That will create the fluctuations. That's an important question.
Igor was asking you about the role of swirl, and I think you basically were saying there was no particular effect due to the presence of swirl in one of the burners.
Well, so maybe it's helicity or something.
Yeah, right, of course. So that is interesting that there's. I mean, but how carefully is that actually looked at? In other words, does helicity play a role?
I mean, was it relating to regarding this case? Yeah, I mean, this is a swirl flame. It's swirl stabilized flame. So I mean, you have a swirling jet coming out here. The swirl number is above 0.5, 0.55 perhaps, something like that. So it's not weak.
No.
You will have vortex breakdown that occurs here somewhere. You will have the development of this recirculation leak. And you will also have this toroidal-shaped vortex that sits like a donut between the flame and the dark matter.
But nonetheless, it's a two-world picture, so it's...
So this is a combination of effects of shear and helicity and homogeneity of turbulences.
Have you got oscillation in this phenomenon?
Yeah, absolutely. I mean, the recirculation region. This is the recirculation region at one instant of time, and it oscillates back and forth, and it changes shape and things like that. So it's affected by the acoustics and dynamics of the system.
Acoustic is some sort of course.
Another question I had was if you could comment. I understand that this comparison that you showed us was done to have a range of cases, okay? But this rough body stabilized flame, probably you could have done that with runs and find chemistry having quite good results and for a much lower price. While the sweet cases are completely different and you would not achieve that. But what do you think? Can you comment on that?
I haven't done this with runs, but I know other people who have done it with runs, and they don't get this agreement.
No.
I haven't done it, but the people that I've seen trying it have not achieved this kind of agreement. There is also dynamic information available. One of the things that they have been able to measure is the temperature with the cars. I mean, you get a transient signal, so you can compute PDF, the probability density function of temperature. So you have a PDF in each of the data points. So looking at comparing probability density functions from the LES computations with the ones that are available experimentally is also a very interesting thing, because then you can separate between different modes of combustion. So you have a bimodal nature, and that is something that you cannot get from that.
Yes.
If I could maybe disagree, recirculation zones typically don't stay very steady. They tend to jump all around. And I would think that in this particular problem, LES is much, much better than RANS, just because now you may not have images. This is a very difficult experiment to run, but if you had images of that recirculation zone, I imagine it would not be ending at one spot, that the length would be changing quite a lot, and if you looked at your LES from shot to shot, you'd probably see some variations, and I wouldn't have much confidence in RANS if you have this recirculation that just ends, and there isn't any geometry that forces it to end at a certain spot. So
Well, it varies a lot. That's
Well,
for sure.
okay, if you look at this backward facing step, you see clearly that runs cannot predict the length of the
But also
thing and
there
so
you
on.
have a very varying.
But we are talking about difference in a fluctuation or of the length of this bubble or the position of this bubble, but these measurements are done for one channel that probably where the effect of what you say would be gone after a while. So also another question is, these measurements are all the way to the wall or are in the are far
It's just across from one wall to
from
the other.
one wall to the other.
I don't think the near wall, there is no near wall resolution experimental.
Yeah, no.
In the last experiment, when swirling is switched off, oscillations should disappear. It was observed this?
I have no idea.
Okay.
I think it's impossible to switch off because
Jet?
easily, but it's too busy. It's rotate.
You lose the vortex breakdown, but
Yeah.
of course also in the jet you have
Jet,
fluid dynamic instabilities.
enough.
Yeah.
Enough.
So is there a direction for these models? Which one is going to be good one for ADS? If I understand,
I mean, these
if I understood your talk, I think you were indicating that thick and thin models is not the way to go.
These are the models that we're using, and if we do engineering type problems like the one I showed before, we typically try to use more than one. So we typically try to do 2 runs or something like that with 2 different models, just to get some kind of feeling for how they work, how different they are. That's kind of an indicator of the sensitivity. I'm not sure. We are not developing really any of these models in that sense.
But
I
whichever
think-
model we use, there is only one physics.
There is only one physics, yes. But I think that we should perhaps look at this modeling issue from a slightly different perspective, using all the information that you have from all the DNS data and the experiments that is available now. And I think some kind of multi-scale method is needed.
Using Martian scale.
Multi-scale method.
Multi-scale.
I mean, the EDC and partially stirred reactor model are very crude multi-scale methods. But something more advanced is required. And there is a lot of work going on with the linear eddy model that we heard a couple of days ago. And Suresh is also coming in a couple of days. So that's a much more advanced model in that sense, where you really try to resolve, at least in one day, the dynamics and the interactions on the smallest scales. But there you simplify the problem by reducing the number of dimensions.
One problem with these with all experiments is that they don't tell you whether you have flamelets or you have no flamelets. And so you can, I think, maybe to address your question, obviously if you have flamelets, you think you might want to use a flamelet model. If you don't have flamelets, you don't. And if you don't know that, it's hard to tell. So maybe we should throw this on to the experimentalists. To characterize any combustion experiment, we have to know whether there are flamelets or not. And
The gradient-based model may do this very good job. Not the model is in general.
general.
If a model is based on the gradient information rather than function.
Okay then, there are no further questions. So, as I said, tomorrow is a holiday, but that's no reason not to come, of course.
Is it open?
And